Oh, hey, well, I'm chit-chatting away. It looks like it is past time. I better get you guys started. And so let me go ahead and pick up where we have left off. And really, as I was saying to you, jokingly but also very seriously, is do you want to know all the answers to all the homework problems for this chapter? This is what this chapter centers around. This chapter, of course, started off with a lot of terminology in terms of magnetic fields, but we eventually got to magnetic forces. What is the force on a charged particle? And we learned a couple of things here that is all summarized, hopefully, in this equation. And we'll expand on it and get another equation before today is over here. But really, everything came from that simple equation, that you would create a magnetic field if you have charges that are moving. So if you had charges that are moving, like we talked about in here we have the electrons that are moving around the atom, that would create a magnetic field. So we have a magnet, what we often call a permanent magnet. Then, if you bring that permanent magnet near another magnet, there's going to be an interaction between those two magnets. And that other magnet could be as simple as one charge moving. And notice it has to be moving. So we came up with this equation. This is where we started applying it. And the rest of this chapter just covers 7 different applications of this same equation, some simpler than others. And we did the following. We said, well, what does an electron or a proton or any charged particle in a magnetic field look like? And we said, okay, it would make a little helix. In fact, maybe I will drop this picture and go back to that one. But this is where we were. In fact, we had kind of this picture of this tokamak, this, storing these charged particles in a little bottle here. And we said, look, as they move around, they are going to make a helix pattern. And their helix pattern is going to be based upon the force. And that force is going to be based upon how fast they are, what charge they are, and of course their magnetic field, and of course the angle between them. And so that's why we get a helix and not just a circle. So we spent a lot of time on that, and so we'll come back to that because we'll keep using those applications. But for that, or after that, then we went to this. We called this the velocity selector. And so what we did is we put this chapter together with past chapters here. You might call this then a capacitor, probably just better to call it a parallel plate here. But we simply said this, that if you have both forces now, if you had an electric force and a magnetic force. So in this case, this is saying you take a plate, you make one side positive, one side negative. These brown lines are supposed to represent the electric field. So there would be an electric force. And that electric force would be the charge of that particle times that field. So in this case, this is representing a positive particle. If this is a positive particle, it would be pushed in this direction, to the right. However, at the same time, because it is moving, there would be a magnetic force to the left. And that's what these green lines are. These green lines are supposed to represent a magnetic field going in. And so if those two forces balance each other, then this particle goes straight through. And the good thing, and maybe more complicated, but good thing about magnetic forces is magnetic forces depend on speed. How fast are they going? So something going too fast would have what I would call too strong of a magnetic force, and it would deflect to the left. Something going too short, or too slow, is deflected then to the right because the electric force is greater than the magnetic force. But something that has just the right speed goes straight on through. So skipping over that one then, we extended, and this is where we left off. We said, all right, if you then take, oh, that's a little picture. Let's go to the full-size picture. All right. Then, if you extend that velocity selector to then continue on into a chamber where the electric field is now gone because the parallel plates now end, but the magnetic field continues on, you will then have a charged particle moving in a magnetic field, which we talked earlier would make it go in a circle. And so as we put these two together, we come up with what we call the mass spectrometer. And I don't have the equation on the board, but I think you remember from last time, the radius then depended upon the mass. And so different massed objects would then land at different spots as they made this semicircle and came to the edge. Oh, I shouldn't have used the word semicircle. Terrible experience this morning. I dropped my son off at school. I go, where do you want to be dropped off? And he goes, take me to the circle parking lot. Well, his high school has, you know, this kind of semicircle where you can come in and the buses come in. I go, well, that's not a circle. That's a semicircle. So he rolled his eyes and left and went on to school. All right. But it's true. Somebody out there's got to agree with me. It's not a circular parking lot. It's a semi. Oh, anyway, all right. But this motion then is a semicircle. And so you go around in a half circle and they land. And of course, the equation we had here was that they would land at different spots. And of course, then we can separate different elements. Maybe oxygen from nitrogen, or maybe uranium-238 from uranium-235. And so we can separate them based on their mass. Well, let me keep going here because my goal here today is to hopefully get through all of these and still do examples, which is a bit ambitious. So let's see what we get. But let's keep extending this because the third one that you will, the fourth example you will see is what we call a cyclotron. These are used for scientists to study nature. They're what we would call atom smashers. Your author has a little animation here and say, again, let's take this whole same idea. Let's take this magnetic force, add it to the electric force, and what is a cyclotron?
I don't think we did the equation for the mass spectrometer.
Oh, we didn't? All right. Let me do it real quick here. For the mass spectrometer, what we're really saying here, maybe I'll go back to that picture so you can keep seeing, but the object is going in a semicircle here, or a part of a circle. Where is it? Here we go. Not that one. That one. But in this region right here, it has a magnetic force on it. So as your author puts, he puts F sub B for magnetic force. He's got the charge, the V and B, and then sine of, and I'll go ahead and put 90 degrees. This will be a nice chance to kind of review this equation. But if you look at the motion of this, the angle theta is the angle between the velocity vector and the magnetic field. So when it first enters, the velocity vector is this way, the magnetic field is into the board. So if I take my right hand and I go V cross B, I'm going to get a force that way. Now if it was a negative charge, then I'd have to multiply by a negative. So anything with a negative charge is going to deflect this way. Anything then with a positive charge, which is what they're representing here, is going to deflect that way. But the point is, as it moves along, isn't my velocity vector and my magnetic field vector always at 90 degrees? So I'm going to put a 90 there and say that's a Q, that's a V, that's a B. So that is the magnetic force. In fact, if we add up all the forces, that's the only force on it, unless you want to say mg from its mass. But these are little tiny objects, and I'm going to say, look, they're going very fast. Ignoring the effect of gravity, it's a very small force compared to these other ones. That would be the total force. And so going back to chapter, I guess it's 6, or I guess 5 is where we get Newton's second law. The sum of all the forces equal to ma. In chapter 6, we learned that the acceleration then would be mv squared over r. And so r being the radius of this circle. So if you have a force that always acts perpendicular, taking you back to your mechanics, then we know it goes in a circle. Or helix in the case if there was some motion along the magnetic field, which we don't have in this case. But if I cross out a V from each side and put R over here, I'll get an MV Q over B. And maybe more technically, and I think this is what we had on the board last time, is we put velocity perpendicular, because only the part of the velocity component that's perpendicular to the field is relevant. So if this thing was moving with the field a little bit, which again, in this case it's not, so V perpendicular is the same as V. But this then would be the equation for that radius. And so as these particles come flying in, we know their speed from the velocity selector before it, because anything that has a different speed would, you know, not get through. And in fact, maybe we should do the equation for the velocity selector also. Back in the velocity selector, we had a magnetic force on it, and we had an electrical force. The fact that it went straight was saying those two were balanced, and we get V equals E over B. Putting that into here, we get an M, we get an E, we get a Q, we get a B squared. So I guess we could also write the equation for the mass spectrometer this way also. But the point here is that the radius would depend on the mass. And so different massed objects being shot through there for the same E, for the same B, and for the same Q would then end up curving around on a different radius. And so you can put collecting plates at different locations. And the one with the least mass would end up a little bit closer. So if this was uranium, uranium-235 would end up being over here. Uranium-238 would be over there. And be one way of separating your uraniums, 238 and your 235. So, and then we would end up with what you would call enriched uranium, uranium with a lot of 235, and stuff to make atomic weapons, or just nuclear energy if we don't purify it too much. And then the stuff left over is all uranium-238, which is a nice, heavy, dense metal, so we'll call that depleted uranium, if you've ever heard that. It's a nice metal used for many things, although it is radioactive, so I suppose you don't want to be around it too much, but its density is really, really nice, and its hardness is really nice. So if you're trying to shoot a bullet at a tank, it's great material. It just goes right through steel. It's just nice and hard and solid, and you shoot a couple thousand rounds a second at a tank, and it goes right through all the pieces on the tank. So there's your different uranium. How'd I get on that? I don't know. Anyways, but that was your question, that the equation. And so this is the equation. This is then the radius of our mass spectrometer. But maybe more than anything else, I should get you to realize, did you see how I came up with that? Did you catch that I used this equation together with my mechanics? Because that's really the big step that I want you to see as we study these 7 ideas, because you're just going to see mechanics after mechanics. And in the past, this is where I've seen students struggle on the homework, is you'll get something like a ball rolling down a hill, and you need to remember torque and moment of inertia and static friction versus kinetic friction. And so all this motion we got to apply back to our mechanics. So it's a good chapter for a lot of reasons. Of course, it does teach magnetism, but it also gives us a chance to review some of our 121. And I think that helps because, this far along, we're halfway through the next semester. And for some of you, it was even a semester before that you took your mechanics. And easy to forget, but you don't want to forget it. So this will force you to review it. And then, like I said, this is a good example of that. Okay, so now going on to something new here. All right, there is our mass spectrometer, but another useful design here is the cyclotron. And the cyclotron is a nice way of getting these charged particles. Let's say they're protons, and you want them to go very, very fast. You want them to, say, slam together, to see what the protons are made out of, or to see what other things nature is made out of. I think I've joked with you guys before, but these whole atom smashing ideas is always kind of interesting to me, because if I bought a car and I wanted to know what the car was made out of, I'd probably go to my garage and get out my socket set and start taking off the bolts and pull out, and hey, here's a radiator, right? Yay! All right, now I keep working on it and dig a little deeper, take the head off and pull out a piston. Hey, here's a piston. And maybe pull out a screwdriver and pry off a ring. Hey! And so, okay, my car has a radiator, my car has pistons, my car has rings on it. Yay, great. But what if these are so small that I can't get a little wrench on it? How do I find out what this car is made out of? Yeah. Pick it up, throw it as hard as I can at the wall, right? See what comes out. And that's essentially what we do. So we try to get these atoms going fast as we can. We send them head on to each other. They collide together. We see what comes out. So you buy two cars, you slam together, hit them. Hey, look, there goes a radiator. Right? You get them going a little faster, and maybe the engine separates. Hey, look, there goes a piston. Get it going a little faster, a little harder. Hey, there goes some rings flying around there. And that's what this is. This is a cyclotron. And if you look carefully at its design, it's pretty creative, I think. It puts together this magnetic and electrical forces. Because what we have is we have two metal pieces. Okay? And those metal pieces are, of course, overall make a circle, or a cylinder, if you will, but they are separated by a small gap. That gap is real important, because this metal plate and this metal plate are then hooked to a big charging station, if you will. And so, if you make this metal plate positive and this metal plate negative, then as the charged particle goes from one to the other, depending on, of course, if you set it up right, let's say I have a proton in here, and so the proton's back in here. If I make this plate negative, what's this negative plate going to do to that proton? It's going to pull it over. And so as it comes over, it would be gaining speed. But notice the opening and the container, because what did we say about the electric field inside of a metal container? It's 0. So the only way you're going to get a field is between the two containers. So essentially what's going to happen is the proton, when it's in here, is not feeling the effect of an electric field. It is not going any faster. Now, in addition to the electric field, you have a magnetic field. And the magnetic field is represented by those green lines pointing up. And so the green lines are pointing up. So as this charged particle is then moving, there is a force on it. And in this picture, they have it going around this way. So maybe I could see if they're talking about a positive charge or a negative charge. I think it was a positive one if I remember right here. But if I take my right hand, and I look at it, say, right here, and it's going that way, and the magnetic field is up, right? V cross B is in towards the center of the circle. So they're showing the motion of a positive particle. And so that positive particle would be moving in a circle. It would be moving in a circle of a radius given by this. Now, it didn't go through a velocity selector, so I'll erase that. This part is invalid. But what it would say is that particle then is going in a circle of radius. And that radius depends upon its mass and its speed. But the interesting part is when it is inside this half of the cylinder, it only has the magnetic effect. The electrical effect has been shielded by the metal. Which, notice also, the magnetic field is not shielded by the metal, which we haven't really had a chance to discuss yet. But it's not, so what happens is the magnetic field is there without the electric field. And that makes it go in a circle. But when it comes around in a circle, and it gets to this little opening here, like I said, if this plate is negative, from here to here it speeds up. And so as it goes from one side to another, it is speeding up. It has an electric force. Can a magnetic force ever make them go faster? No, right? That was part of our discussion, right? A force that is perpendicular to the motion of the electron does no work. And so we cannot use a magnetic field to ever get these things to go faster. Now we can use the magnetic field to control them and make them turn and make them hit certain spots or keep them in a bottle, but we can't make them go faster. So we need that electrical part to make them go faster. We need the magnetic part to control them, and that's what this cyclotron is doing, because then as it goes from one half to the other, and it goes from here to here where it goes a little faster, because it goes a little faster, it is now going to have a slightly bigger radius on the next lap, if you will. And so every time it makes a lap, it's going a little bit faster. And so you can see it's spiraling out faster, 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 faster. And every time it goes inside of each metal chamber, the electric field is zero, but the magnetic field is not. And so eventually it goes faster and faster until it exits out here. And I think your author does a good job of showing that picture. Plus, I really like this picture. Here is the first cyclotron built. I wish you had some kind of scale on here, because it's only about this big. And they talk about, oh, here's the science's first little cyclotron here, as it kind of goes back and forth. And here's today's cyclotron. He doesn't have one in your book, so I grabbed one. Here's an aerial shot of CERN. Here's today's cyclotron, as it takes 17 miles to go all the way around. So a lot bigger by far, and obviously a lot higher in terms of energy. And so these things are ripping. In fact, I think I like this picture too. Here's down inside. Here's this giant tube that is 17 miles in circumference as we go around, and I guess that's how you get around inside, cruising around.
So you said the magnetic fields don't accelerate particles?
Right. How do I know that?
And how do they accelerate particles?
With an electric field.
Okay.
Yeah. Yeah. Now, they don't quite have two big plates. You don't have a plate that is whatever the diameter of circumference is equal to, but they will have areas within here that would have like a plus minus. And so as it comes, or minus plus, if they're coming this way, then from here to here they'll accelerate it. And so parts within the tube would have charged plates that you can turn off as they go by and then turn on. And they do other things. That's definitely an overly simplification of how complex a $10 billion machine is. But that's, the cost of this crazy thing. So there's your next application, if you will, the cyclotron. Well, going down the list, here is what I would call a CRT, which stands for cathode ray tube. And again, your author does a good job here. Maybe the best thing I could say is this is an old-fashioned television set. Although, as you'll see, it still has some nice usefulness. Trying to... thought he had a picture of a CRT. I see this one, but that's not the one I was after. Doesn't he have a... oh, there it is right here. This one here. Okay. And so, if you do something along these lines, and you start here, and what you do is you set this up, and you say, all right, I am going to make this metal plate very negative and this plate very positive. Well, I happen to have that here. This is our little CR tube, CR tube here, our CRT, is that I can hook this up to this power supply, which is about 10,000 volts. So this is going to get very negative over here, and this side is going to get very positive. And if you get it enough negative, what do you think will happen to these negatives that accumulate on this plate, given the fact that these plates over here are now positive? Yeah, it may, if you get enough voltage here, actually rip them off the metal, right? And send them on through. And so we put them in a glass tube so it can be evacuated so we don't hit any air molecules along the way. But if you turn this voltage on enough, what's going to happen is these particles, called electrons, are now going to come off and head towards then this positive plate. And hence they are cathode rays, because they are then coming from the cathode and swinging over, depending on your definition of cathode, going to the cathode. And so this is why they called them these cathode rays. Early scientists did not know that they were electrons, but you know that, at least that's what I'm telling you now, is that these are simply electrons. And so what will happen is they fly through the tube. Now in our case, they go across and they hit, well in this case, they go across and they're hitting this glass tube. And if you remember me showing you the fluorescent light yesterday, do you remember when we took the electrons coming from the Van de Graaff and hitting the fluorescent tube and it gave off light? And I used an example of saying these are the northern lights. The same thing will be happening. If these electrons hit material, say phosphorus, it will give off a green color. And that's what this big white screen is here. This white screen has phosphorus on here. So if I turn the lights off here, and I turn this on, let me just get my magnet ready, there we go. I can hopefully get a green strip. Not that the electrons are green, but what happens is as these electrons go ripping through, when they hit the phosphorus, they give off a green color. And so sure enough, you will see a green stripe across there, because in this case they go through a slit, and then mine only has one, not two of them here, so that then when I put a screen out here, I can, this part of the slit hits the first part of the screen, and as the screen arcs over, these electrons hit that, and so I got a strip along here. But what happens if I bring a magnet near those electrons? Won't it deflect the electron? And if I turn it around, won't it deflect it the other way? And so, again, same basic principle, that the force is applied to these electrons. And we can then push them sideways in part of a curve. And you can control them. And so you can see in this picture, they're trying to show you that on the side here, we got little coils of wire, and as they pass current through them, that will create a magnetic field, and that magnetic field will then deflect the beam, and we can control where the beam lands. And one of the most common, yet actually in today's LCDs and LED screens, it's getting less common, but this you might recognize as an old-fashioned television, and this is how you got an image on a screen. You made cathode rays. They hit the screen, they hit the phosphorus that's on the screen, and they gave a certain pattern. They gave you your picture. Yeah.
What happens to the electrons after they hit the picture?
Oh, well, in this case, so many will accumulate that they will move, and it's not paper, it's actually metal with phosphorus on it. So when they hit, they're embedded in the metal, so they conduct along the metal, and on this case, way over here, they come off and they finish going over. So they make a full electrical circuitry, if you will, where you might say this is a very high resistance. So 10,000 volts, maybe divided by 10 million ohms, and that would be the current in there. But it's a full circuit, and I just have some resistance. And so here's supposed to be a kind of a simple picture of a TV screen. The electrons start way back there, they go firing through, and if there was no force on them, they would hit the center of the screen. But to make an image then, what you need to do is to control where they actually hit. I guess I could turn the lights back on now. But here is an older, simpler TV. Okay. That then has these electrons coming from the back racing forward. But of course you probably know that these older screens, TV screens, these CRT tubes, they have some thickness to them, right? They're not exactly the type you hang on a wall, right? Of course, the smaller the screen, the less depth you can have. But as you try to make big screen TVs, these things are getting bigger and bigger and thicker, and glass is getting heavier. Because again, you have to evacuate all of this. And so as you evacuate this, you've got to make it a thick, thick glass. So the reality of trying to make an old-fashioned TV 35 inches, I guess, is possible. And I think there are some that big. But getting bigger than that, just extremely difficult. So as I think you know, we have moved away from making large screen TVs with these CRTs. But this one was turned on purposely. There's no image here, but you can see it's white because what's happening is the electronics inside is controlling this beam, and to make an image, you shoot the beam up here and you scan across, making one row, making another row, making another row, making another row, making another row, and so you'll go all the way across, making, depending on your resolution, but we'll do old school, 512 lines. And so you will get an image out of this if you turn it on and off at the right places. So you will get on, off, 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 on, off, on, off, off, on, off, right? And so it'll scan all the way across the screen and every line, and it does that in a 1/30th of a second. So there is your first picture. And then it does it again in a 1/30th of a second, and then again and again and again. And so that's what's going on inside your TV. So you can see it in action. It's kind of fun to watch. Let's take a magnet, a good size magnet, and we know that this has a North Pole and a South Pole. And so if I was looking at the field from here, the field would be going from north to south. And so if I hold it this way and bring it near the screen, shouldn't that deflect the electrons? Right? And so sure enough, they get deflected, in this case, away from where they're originally designed to go. And so maybe in this big class, I'd have split it in half. You guys, so you can see, right? If I do that, it blocks them. Right? You guys over there, if I do this, it kind of blocks them. Unfortunately, my magnet blocks your view also. But watch this. What if I were to hold the magnet this way, so the field from this, which is going out and then arcing around, electrons coming straight in, this would be like the northern and southern lights we saw the last time, right? Don't the charged particles have no force when they go this way? A lot of force when they go that way because they're going perpendicular to the field. But when they're going this way, they're going with the field. And so this is really hard to see because I'm going to block the what you can see with the magnet. But if I hold the magnet right here, can you see right behind the electron still hit? It blocks it everywhere else. But right behind the magnet is where they're coming in, and there's little to no force. It's the ones that are off to the side. And so there's the design of it. Which, by the way, if you're wondering why I use the black and white TV, which aren't easy to find. Is because a color TV actually does this 3 times. It's got one beam for your red, one beam for your green, and one beam for your blue. And in order to separate the red, green, and blue on the screen, there's a metal wire mesh in there. And when you bring a magnet near it, then that metal mesh can get magnetized. And then when you pull it away, it's still magnetized. Speaking of my same son, when he was younger, the same thing happened. He had some of my magnets he was playing with and came running into my study. Dad, have you ever seen what happens when you put a magnet on a TV screen? Yeah, so I went out in the living room, and he had put the magnet all over the screen. And then left it, and then the metal pieces inside were now permanently magnetized. And so those parts of the screen, none of the electrons hit. So they were kind of red and purple and black. And so you kind of had to watch TV with 3 or 4 holes in it there for a long time. And fortunately, and most monitors and TVs have, in the setup, they have what they call a degauss button, where that's what it's for. It's okay, sometimes something's going to happen, and so you need to go to the setup menu and hit degauss, and it'll degauss the screen.
So that why when for the old TV you would put your speakers next to them?
Yes.
Completely like distort the images?
Yeah, exactly. Again, speakers use a strong magnetic field. So computer speakers are actually shielded. They put the magnets inside, and then they put a kind of a mu metal around them to protect and to keep the field inside and not affecting your screen. So it used to be a big deal. Of course, now most screens aren't CRT tubes anymore. I know I used to always study this way. I'd put my cell phone on my own old CRT tube. Because before it actually rings, information is going back and forth from your cell phone, and it's passing things like the time and the phone numbers back and forth, and it'll ring 20-30 seconds after it starts. Well, maybe that's a little long, but it does ring afterwards. But when I always had it sitting on top of my monitor, I could be working, and when I saw the screen dance, like, okay, something's getting ready to call. All right, and then it would call. So it was. Right, and then right, good, and you can pick it up on the stereo, yeah.
So what causes the screens to burn in if you don't use a screen saver?
Oh well, then these electrons are hitting that, I'll call it phosphorus, but they use multiple different materials so that you can get your different colors, your red, greens, and blues. But you got to remember, you're hitting them pretty hard. Okay, so they begin to wear out. And they don't have that uniform pattern. So if you had the same image there, you're going to physically wear out the thickness of the material. And so it'll be in a different thickness at different times. And a consequence of that, then you have an image. I mean, that's what an image is. If you held up a piece of paper and you kind of scraped the paper, right, where it's thinner there, when you hold it up, you'll see where the more light comes through and not. It's thinner. And so you have a permanent image embedded because of the wear off of it. So that's why screensavers were invented, so that whatever image is there keeps moving around and you don't burn out the same image. Yeah. I don't know if that's really even relevant anymore with an LED screen. Do they?
LED screens with an LCD LED screen.
Okay. There's no full LED screens yet?
Well, LED is what they use for the backlight. LCDs control the pixel. LCD don't burn out.
Okay. Yeah, they don't burn. Yeah, see, I wouldn't think they would. But haven't they gone? The older ones, well, not the older one CRT I'm talking about, but then they went to LCD, and now aren't they all LEDs?
They went to LCD, LED, and then OLED for the phones, but they don't have large OLED
Oh,
phones yet.
okay.
They went to plasma.
Well, yeah, and then plasma I kind of consider this kind of intermediate step, if you will, is because we wanted a big screen, you wanted it flat, but we couldn't make, oh yeah, and the DLPs, yeah, I forgot about those, but those are kind of an intermediate step. But plasma has the same problem, is that the material in there, you're making a little plasma, and the explosion of that plasma wears out the phosphorus. And so those plasma TVs don't have much of a lifetime with them. So they're, and getting harder and harder to find a plasma TV. And DLP, I forgot all about that. I haven't seen a DLP in 5 years or something. Yeah, that's kind of a nice intermediate step. Anyways, I hope you got the idea of what the CRT is. All right, let's keep going. Hall effect. Here's a nice one because it has some very interesting applications we're going to use in the lab. Let's look at this structure here for a moment. Scrolling on down towards the end of the chapter, your author kind of gives you this picture here. And he says, let's do this for a moment. Okay? And it was actually Hall's experiment here that finally answered an age-old question that I've been telling you since the beginning. If I hooked up a battery, and so here is my battery, plus, minus, and I take it and I run a wire, and in this case, Hall's answer is he's going to take a rectangular piece of material, okay, and say, all right, put a magnetic field And so you can kind of see in this picture, he's got a magnetic field going perpendicular to this rectangular piece of metal. But the long question at this point had been, if we call this the current I, and we define it as dq dt, are positives going this way, or are negatives going this way? Well, I think you know the answer because we've been telling you since the beginning. What's happening? Yeah, these negatives are actually going this way. But it was this experiment, Hall experiment, that was the conclusion of, okay, now we know. Let's take a look at this. And this is what he's trying to say here. It says, look, when you pass a magnetic field perpendicular to this bar here, okay, if the current is going this way, so in this diagram we got the current going this way, we have two options. Option one is that the positives are moving in the direction of the current. Or option two is that the electrons are moving the other way compared to the current. Fair enough? But if you put them in a magnetic field, let's take a look at the force. If it is positives that are moving this way, then if I go V cross B, taking my right hand, V cross B, I get up. And so if positives are moving, they would be forced to this upper edge. And this upper edge would start to build up positively charges, while the bottom edge would be left without positive charges. So we would say this edge is positive and this edge is negative. Now on the other hand, if negatives are moving, so here's negatives, they would be going this way. So V cross B would be down, but again, since they're negative charges, the force would be up. And in that case, negatives would accumulate at the top. And so there's a difference between whether positives are moving and whether our negatives are moving when we add the magnetic field. You don't have that when we were only dealing with our circuitry. So Hall has a very clever idea here. He says, look, let's actually measure the voltage sideways on this bar. Here's kind of his voltmeter setup like this. He says, look, let's make the current go through this metal bar, and so maybe here's the battery out here and it goes around, something like that. But this, what he'll call a delta V, this is the voltage between the top edge of the bar and the bottom edge of the bar. And so the question will be, do I get a negative reading when I hook them from top and bottom, or do I get a positive reading when I hook them from top and bottom? And so let's run through the math here. The math would look something like this effect. Let's put, as I said, this equation together with our electric fields, and let's see if we can come up with the Hall effect. And what we're going to call the Hall effect probe here, and we're going to use in lab, is we can find out whether we get positive or negative. And you can see in his meter, he gets a negative reading, and that tells him that negatives are moving through the wire. And so there's the first conclusive proof that the negatives move.
So what if you were using a liquid conductor? Would anything be different? Would the positives move?
Yes, the positives would move. The negatives would move. And would they come out to be the same and have no net? I'm thinking yes, but maybe we can see that if we go through the math. The math here in just a second. They are going to have a different mass, but I don't think that matters. So I think you would get no voltage if they were both moving, equal amounts. If you had more of one than the other, then you would have, if you had more negatives than positive, you would get the voltage like this negative. If you had more positives, you'd get the other way around. But here's his argument. His argument is that if you took this metal plate here, and as he's trying to say here, what's going to happen, and I'll just use the negatives here for a moment. The current is going this way. The negatives then are going to start to get pushed up. So you get negative, 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 negative. Again, because here's this electron moving this way. So I've got it moving along, which we'll call its drift velocity. I've got a magnetic field going into the board. So I'll put a little X with a B next to it. So this is my magnetic field. So if I go V cross B, I get down. Obviously times a negative, I get up. And so there would be a magnetic force pushing them up. Fair enough? Which probably would mean I would be lacking some negatives down here. So all the moving negatives get pushed up. However, is this going to happen forever? No. How come? Yeah, exactly. Once I get negative ones up here, the next negative one's a little bit harder, right? And so what's going to develop here, and maybe I'll change colors here, what's going to develop is an electric field. Right? And that electric field is saying don't push more positives up. And so just like our velocity selector, we have the same thing. What ends up happening is we have a balance at some point where the force pushing them up, Q, V, D cross B, magnitude, is the same as Q, E. And so as I calculate this out, I get this, if they're moving perpendicular to the field, for the magnetic force. I get this for the electrical force. The Q cancels off, and just like we had for the velocity selector, I would get this relationship between the E field and the B field. In other words, for a given B field, if I set this magnetic field to say 1/100th of a Tesla, and I turn on this current, which the current defines then what their drift velocity is, then what's going to happen is enough charge is going to build up until the electric field equals that amount. And at that point, the current or the electrons just keep moving without a deflection, but the top and bottom remain charged, and that's why I can take a voltmeter and measure that voltage. And in fact, how would I get that voltage? What your author calls V sub H, the voltage from the Hall effect. And so that's what this meter is trying to say. He would set it up across there and say, okay, that voltage then would be the strength of the electric field times the distance separating on this rectangular plate. And I'll use a D. What does he have up here? He doesn't have anything in that picture. I thought he had a D in one of these pictures. But just yeah. So there would be the D here in this picture. So that would be the voltage. Now if we continue on to what we just did, that electric field then would be VD times B times thickness D. That would be the voltage. Now let me take you back 2 chapters. And I'll say it again. Did you cut how I started here? And then I went all the way back to chapter 23. Now I'm going to go back 2 chapters. How is current related to drift velocity? They are proportional, right? What were those proportionality constants? Right? And so going back to chapter 27, when we have a current flowing, we said that the current was related to its drift velocity, the area that the current is flowing through, the charge of each particle, and the concentration of them. How many particles per volume do we have? So if we place that here, we can get the Hall voltage then would be equal to, in fact, maybe I'll just do a little bit of math here. VD then would equal to the current divided by the N divided by the Q divided by the A. And so making a substitution in here, I get an I in the top and I get an NQA down in the bottom. And that then would be the voltage. So obviously the voltage does depend, of course, on all these other factors. But as I said, you can hopefully see that whether you get a positive, in fact, there's two things I want you to see here. You can see that whether this is positive or negative is related to what is the charge that is moving. And so as I said, Hall's famous experiment is just that. Overwhelmingly proof that what's moving is the negatives, not the positives, right? And so at least I should say in, say, copper, that's what's going on, because we do have other materials and other things that are going on, and other ones that can be a bit more complex. I kind of want you to see the reverse of this, because this is what we will be doing in the lab. Couldn't I then rearrange this equation to say B equals? Wouldn't B equals the concentration of them, the charge, the area, the voltage you get from your Hall meter, the current you are sending through, and D, the width of this metal strip? Because here's what you are going to do, and this is, I think, like I said, probably more interesting to you than Hall's experiment that's, okay, which is moving, positive or negative, although I hope that's interesting in itself. Here's the practical side. Couldn't we use a voltmeter to get the magnetic field? And that's what we'll be doing. We will have this little tiny device, and so you can see the connections from the equipment you've been using in the lab. This obviously goes into our ULI, and this is our Hall probe. And in this Hall probe, you will see a little white dot, and buried under that plastic white dot is a metal strip. And then that voltage is fed into the computer. It's not much voltage, so this is a little amplifier. So we amplify the voltage, we send that into the computer, and given all these other factors, we can then say, all right, we've got the voltage. From that, we can get the strength of the magnetic field. And so we are going to take this and put it here, and we're going to put it here and say, okay, what is the strength of the magnetic field from this bar magnet? But what I want to make sure you see is all this was derived with the current perpendicular to the field, wasn't it? So your biggest challenge in the lab will be to remember that you have to take that white dot. You have to know something about the shape of the field. In this case, here's the North Pole. It's coming from the North Pole. If I wanted to get an accurate reading, I would have to align it like that. This isn't going to work, right? This isn't going to work. It needs to be this. The field needs to be perpendicular to the current that is carried through that metal strip. And so, careful in the lab, and we'll mention that on the day we do this lab, which it's not next week, but the week after, yeah.
Could you use a device like that to measure current without breaking the circuit?
Oh, yes. Sure. You could also do some simpler other things with Faraday's law that we will, if it's an alternating current, which is what we will do actually in not the next chapter, but the chapter after that. And so you don't have to actually, as you said, break open the current. Those meters are really nice, where you have a wire and you just come and you hook around the wire, and it reads the magnetic field caused by the current in that wire. Okay, but this is an external magnetic field, so this is a little different than what we will do. Well, finally then, probably the most, I shouldn't say most important one, but certainly the one we're going to spend the most time on is this last one here, is the electric motor. Let's do this for a moment. Let me turn off this Hall probe here and put this picture on the board. Maybe I will start with simply this one. Okay. What if I just have a segment of wire going through a magnetic field? Now, at first I will say there's no current. And you've already seen this setup. I might as well start to set it up again here. But if this is my magnet and this is my wire, if I put this wire in the magnetic field, And at this point, there's no current, but I soon will. So I'll just hook this side negative for a moment. I will hook this to our tap switch that we've been using many times and finish the connection here. So in my case, you may say, all right, there would be no force. Well, maybe I should ask, why is there no force? Yeah, there's no current yet, right? To get a force, we have to have a movement to our charge. So are there a bunch of electrons in this wire right now? Yeah. But they don't have a net drift velocity. They're going equally left and equally right. Okay, so there's no net force here. But when I tap this switch, there is. And in the way I have it set up, which way would that force be? Well, it looks like the electrons, if I follow the electrons, here's the negative on this battery. It looks like the electrons then are going to go this way. All right, which way is the field? Okay, here's north to south, so they're kind of angled out towards you. So if I take my right hand and I go put my fingers towards V, close it towards B, that's V cross B, but now these are electrons, so the force should be times a negative number, right? And so the force should be down. I don't want that, so how about if I switch it for a moment? Wouldn't that make the force up? And maybe I'll just test it again. Yep, there's that force. But definitely sends them upward. Okay? Can we change this equation into an equation that has current? And then current into one that has voltage and resistors? In other words, can we extend that to last chapter where we did our circuitry? And I think we can. So in other words, if I told you that this was 12 volts, and I told you the resistance in this wire was 1/10 of an ohm, couldn't you tell me the current? And from the current, couldn't you tell me the force? And so this last part is an extension by saying, look, all right, imagine this wire. Imagine this wire having not just one electron moving, but thousands and thousands of electrons moving. What would the force on that little section be? So let's call this little section a length delta L. There is my length. Small little section of wire. Delta L. I would say this, that if I was looking at the force on just one of them, I would get that. Fair enough? That's the force on one of them. However, I don't just have one electron moving, do I? I have a bunch moving. So let's just say that there are n electrons within this little section. What do you think the total force would be then? Well, would it be okay if I write it that way? If they're all going the same speed, they're all going the same direction, if they're all in the same magnetic field. Now you may say, well, wait a minute, maybe they're not in the same magnetic field. All right, but I am going to say this. What if I take the limit as delta L goes to 0? Would you agree that on a limit, as they get smaller and smaller and smaller, ooh, I think I see some calculus coming. As they get smaller and smaller and smaller, would they all be going roughly in the same direction? Would they all have the same magnetic field in the limit that I get smaller and smaller and smaller? And in fact, their speed is probably best illustrated by their drift velocity, right? And so that would be the force on that little segment. In fact, maybe to illustrate it a little bit better, can I go ahead and put a delta F? Meaning that this is a little force on one little piece of the wire. Because I'm sure some of you are looking at this going, well, wait a minute, doesn't there have to be more to this wire? Yes. Doesn't there have to be another section? I mean, don't you have to have a whole closed circuit in order to have current? So really what I'm talking about is a very small limit piece of wire. And therefore that would be a very small amount of force on a wire. The whole force on the wire I would have to integrate this up, right? And I would have to add up to find what is the total force on this wire. And so we're going to do that here. And let's just make that same statement we had before. Isn't the current equal to the number density times the charge times the drift velocity times the cross-sectional area? Right? That's the one we just did for the Hall effect. And so if I do that substitution here, let's take a closer look at this. What was n again? I know it's been 2 chapters ago. Lowercase n. In other words, lowercase n and uppercase n are related, aren't they? What did lowercase n mean? Yeah, the number per volume, right? And if I look at this little section of wire, and maybe I should give it some thickness here, this would be the area, right? And if we're talking about a length of delta X, or delta L, wouldn't this be A times delta L Q VD A? And then doesn't the A's cancel off? And in fact, maybe now you're beginning to see it. NQVD. Isn't that what I have over here? NQVD. So this small little force is equal to what? Well, maybe I should put current and delta L on that side, and that would equal to NQVD. And so if I take all of these and substitute this, I get I delta L cross B. Now, maybe to make this more complete, I should pay attention to my vectors. This one has drift velocity with a vector. And over on this side, I guess I've only been doing magnitude. But is it fair to say that the drift velocity would be in the direction of the wire? So magnitude, it works right. But I'm going to then invent or comment that delta L will be now a vector. It's not just the length. It's not just a number. It's not just a scalar. But if I think about it this way, it's a scalar with a direction. And the direction is just the direction the little chunk of wire is pointing. But my point is this now. When I take the limit as delta L goes to 0, this equation then becomes a little bit of force, there's my calculus, with my vector, equals to the current I have in the wire times a little bit of length, dl cross B. Right? And that, I'm hoping you see, is really the same as this, but can be a little more useful if we are talking about currents, because then I can say, okay, I have a battery. The battery is 12 volts. I have some resistors, let's say 1 ohm. That means I have 12 amps when I hook it up. How much force is on that wire? And so the total force will then be the summation of the entire force along that wire. And maybe I should box that one, I don't know. This is the differential form. This is what we call the integral form. But this would be the total force on that wire. In the simplest case, and that's what this screen is hopefully representing, In the simplest of cases, this is what I have. If you look at this very simple case, right now I have a wire, and if I look at the section from here to here, I think it's fair to say that along that section, isn't the current the same everywhere in that wire? Which at this point is 0 because I haven't touched the switch. But once I do tap the switch, isn't the current going to be same everywhere in that wire? So even though this is in the integral, couldn't I pull that out in front? There's no nodes, right? All right. So everywhere along this wire, same current. I'll even do you one better. In a simple case, wouldn't the magnetic field be the same along there? Now, I doubt if it's true for this wire because the magnetic field is very strong in here and gets weaker as I move out. So my setup is probably not idealized like this picture. But this picture is trying to say, look at the concentration of the magnetic field lines. They're the same, meaning we have the same magnetic field. So putting that on the board, the special case, if I is the same everywhere on that wire, if B is the same everywhere on the segment of wire that we are dealing with, and if the angle theta is the same, and again I think it is the same, isn't it? What is the angle? 90 degrees. The angle between what? Yeah, between the magnetic field and the wire. Did you catch that? That's what this cross product means, right? These are the two vectors. The angle between the wire and the magnetic field. Okay? And so that's a constant. And if all of those are a constant, then the total force on this wire is then simply an I can be factored out, a B can be factored out, the sine of the angle can be factored out, and in this case it's 90 degrees, and what I'm left with is just an integral of dl, and then that would just be the length of the wire. So the simple case, this would be the force on that section of wire. And that's what you've been watching for the last couple of days. Me tap this switch, and it puts a force. And of course, it's enough force to lift the wire up and move it across, so you can hopefully be convinced that there is a force. Your author does this. He says, all right, and before I put the picture up here, what if the current goes this way as opposed to this way? Let's talk about current going up. What direction would be the force on this wire if the current went up? Would it be left or right? Would it be out of the board or screen into the screen? Would it be up? Would it be down? I mean, of all 6 of those directions, which is it? Well, I'm hoping we can rule out in and out of the screen right away, because doesn't the cross product say that the direction of the force has to be what? Perpendicular to what? Both the magnetic field and the wire, okay, which is the velocity of those charges in there. And so as I look at this, what direction is perpendicular to both? It's either right or left, right? If it goes up, well, that's in the direction of the wire. That's not perpendicular to the wire. If it goes down, same reason. If it moved out, well, that's in the same direction as the magnetic field. So the only way you can be perpendicular to both is if you either go left or right. And so that is what our force direction is limited to, left or right. And now I have a cross product, a vector cross product. How do we do vector cross products? That's what our right hand is for. I grab this again, if you remember from 121, although I've done it enough here, this makes a nice example of a cross product. If this white one is the first one and the black one is the second one, this is the direction. Notice it's perpendicular to both of those, no matter how you hold it, right? And so if my fingers go towards the first one and I close them towards the second one, my thumb gives me the direction. So in this case, the first one listed is L. So using this white one as the first, I guess the white one would go something like that, right? The black one would be something like that, right? To hold it in terms of L cross B, I guess I have to have something that looks like that, right? Where I would put my fingers in the direction of the first one, close towards the second one, then the force would be that one. And so L cross B is that way, right? Notice, unlike this one, I don't have to say plus a positive charge or plus a negative charge. That's already buried in the eye. So that's kind of nice, right? And so if you look at this, and then the next picture here in your book shows it. It shows the force on these when there's actually current flowing. And so they say, all right, look at this picture. When current is flowing up, I cross B goes that way, and this wire bows out in that direction. Whereas over here, I is down, so if I take my right hand and go down, there's I cross B, I get that way. And so there is a force on this wire. Now, if that made sense to you, let's extend this one step. Because in any real circuit, we have to connect the whole loop. We have to have something that looks like this. What if we had a rectangular wire, which is kind of overly simplified? Maybe I'll say there is a small battery buried in here. Actually, I guess what I'm going to do in a minute is do something like this. And this end is going to hook to a positive terminal on a battery. And that's going to be hooked to the negative terminal on the battery. But taking the battery out of the picture for a moment, let's look at this picture here. Let's look at this one here. Okay? Here is a rectangular loop. Okay? What would be the total force on this rectangular loop? Well, in that picture, the current, and let me just see if I can take a look at there, they call the top section number 1. So the current is going this way in section number 1. The current is going down in section number 2. It's going across in section number 3. And it's going up in section number 4. Okay, so these are the 4 sections. And the places where we have 1, 2, 3, and 4, I pretty much could use this equation. Fair enough? Because they're trying to say, during that section, don't you always have the same angle between I and B? Isn't the I, that is the wire, always going in the same direction along each section, 1, 2, 3, and 4? And the magnetic field, they're trying to say, is a constant or uniform magnetic field. And if you watch this one carefully, it's a lot of work to get a very boring answer. Because what do we get? We get 0. We get 0 force on this wire. I mean, watch. If I look at this carefully, let's look at number 1. Hopefully number 1's the easiest. How much force is on wire number 1? 0. Why? Yeah, it's parallel, or maybe you'll say anti-parallel, because the field's going that way and the current's going this way. So I would say it's 180 degrees. But if I put in my equation, what sine of 180 degrees? 0, right? And so there should be no force on any of the wire up at the top. And that makes sense, because those electrons are moving in the same direction as the field. Remember, we only get a force when they move perpendicular to it.
Wouldn't it start spinning?
Oh, it's going to spin.
So why is the force 0?
Forces don't make them spin. What makes things spin? Torques. All right. So it's not going to translate, but it is going to rotate. Exactly. All right. So that's why I said the first step's kind of boring. No translation. The next one's very exciting. It rotates. Absolutely. All right. So just going through this, then on this part of the wire, okay, we've got a current going down. Again, looking at this, I is going down, B is going this way. If I take my fingers, I goes down, B goes that way. I would get a force coming out of the screen, if you will, towards you. And so I'll label that with a circle with a dot and say on this section of the wire, there is a push on that wire coming out towards you on the screen. As I get to section number 3 right here, across here, section number 3 is, well, maybe I should ask you guys, what's the force on number 3? 0, really for the same reason. This time they are parallel. This time I would put an angle of 0 degrees instead of 180, but either one would give me a 0. So there should be no force on that section of the wire. And then on section number 4, current is going up, so I'd take my right hand, I'd put my fingers up, I'll rotate my hand to close towards the magnetic field, and I'd get into the board. Okay? And so I'd get a force into the board. And if you look carefully at this very simple rectangle, the force on number 2 and number 4 are really the same. Don't they have the same current in them? Assuming that the same magnetic field extends all the way across. The angle, maybe I should ask, what's the angle? 90 degrees, right? See that? Okay, three-dimensional picture. And the lengths are the same, which they've got them labeled as A in that diagram. And so I end up with one force coming out of the board, one force going into the board, and so I would say if I add up all the forces, which set equals to MA, I have a 0 force equals to MA, or A equals to 0. And so that's what I meant. This thing's not going to translate. It's not going to move from one place to another. It's not going to go to the left, the right. It's not going to go up. It's not going to go down. However, as you quickly observed, what is going to happen? And I think you might see this a little bit better on a sideways view. Sideways view is if you look at this loop and tilt it upward, and so my little model is right here. Question?
So as soon as it rotates 90 degrees, the one on the top and the bottom wouldn't be parallel anymore, would it?
Ah, hang on with that question. Good. But at this location, what I had here was a rectangular loop where what I can do is take my power supply, and if I hook my power supply right here, this part, what I'll call the brushing, actually makes an electrical contact here. The current goes down through and around the rectangular loop. And these colored pieces of wood are supposed to represent the magnetic. Obviously, this is not a real magnet here. But there's the North Pole, there's the South Pole. So the field is going across here, current going down and across. This wire has a force that way. This wire has a force this way. And wouldn't that then rotate it? And this picture is having you look at it in this direction. And saying, let's look, head into this. And if this wire then is being pushed up, and so the purple color is the current going at you, so here's a current going towards you, then the force, what they call number 2, is up, and this one, the current is going into the screen, force number 2 is going down, and so I would get a rotation like that, at least at first, right? And so again, the net force is 0. So this wire does not move this way or this way, but it does rotate. So let's take this one step further and better. Let's look at the sum of the torques. Does that come out to be 0? No, right? And so now again, I'll say it, notice what I'm doing. It's just this equation applied to our mechanics, right? I looked at the forces and realized this thing's not going to translate. But in a second, I'll realize there is a net torque, which means it's going to rotate. And so it does have a rotation. So I would look at it, and in this case, it is designed so that the wire has the ability to rotate around an axis down the center, as you can hopefully see in this design here, is it can spin. And it can spin if there is a net torque on it. So let's calculate that net torque. I should have a torque from wire number 2, and I should have a torque from wire number 4, and that should equal to I alpha. Let's do torque from wire number 2. It's going to take us back a while. I should probably write it as a vector and say, all right, how did we calculate torque again? R cross F, right? It's a cross product. Now wait a minute. It is another cross product. How did I get the force on the wire? A cross product. Don't mix these two cross products. I got a cross product here, which is giving me the force. That is the cross product between the current and the magnetic field. In addition to that, I have a torque, which is coming from another cross product, which involves the angle between the R and the F. It's quite possible, and will happen. Is the angle between the R and the F the same as the angle between the L and the B? No. And so don't mix these two. Okay? I mean, let's run through this so that hopefully we won't mix it. But I'll start with the simplest case. And the simplest case is when it is in this location. It'll move in a second and then it'll get a little harder. So we got to talk about that. But in this location, before it has moved, I can hopefully get the torque. Because in this case, what would the R be? Well, it'd be from here to here. Which, if you remember in the diagram we had before, and your author shows it here, he called this whole length from here to here B. Fair enough? Maybe I'll hold it back this way. But he called from here to here B, and he called from here to here A. So from this pivoting axis over here to this wire, isn't that B over 2? And for that matter, this one is B over 2. So when I go to calculate this, I would put, okay, torque number 2 would have a distance of B over 2. The force number 2 I get from this, right? And so I will call that the I, the B, the sine theta, and L. Now maybe I should fill these in a little bit. In the configuration I have, what would that theta be? It's 90 degrees, right? Okay, so right now, that's going to be filled in with a 90 degrees. And what would L be? That's the length of the wire. So it's from here to here, right? Isn't that the A? Okay, so that would be my A. Okay, so there's the distance. There's the magnitude of the force. But then I have to multiply it by what? Sine theta again. The same theta? No, right? There's two cross products here. Okay? And so this, as I said, is the cross product I get from the magnetic force. This is the cross product I get from the torque. However, in this case, the simplest case, what angle is that? Well, isn't this R? And isn't this F? So isn't that 90 degrees? So they're both 90 degrees, but I want you to see they are different 90 degrees. Let's look at the first one again. 90 degrees. What 90 degrees is that one from? The wire in the magnetic field. So which way is the wire? Towards you. Which way is the magnetic field? That way. So the 90 degrees I'm talking about is a 90 degrees in a horizontal plane. But then when it came to the torque, I'm talking about this 90 degrees, which is the 90 degrees in a vertical plane. So again, in the simplest case here, they're both 90 degrees, but I don't want you to even think that they are the same angle, and that's why I'm taking some time here to say, okay, in this picture, they are 90 degrees. That's soon going to change. But in the simple one, they're both 90 degrees. And simply put then, I get B times 2 times I times capital B for magnetic field times length A, and sine of 90 and sine of 90 are 1. And that's the torque from wire number 2. Now, would it be okay by extension if I just jump to the torque on number 4? What are you going to say about the torque from number 4? Isn't it the same amount? Right? And so this is the magnitude of the torque from number 2, but I claim it's also the same as the magnitude from number 4. So the magnitude of the total torque would be twice B over 2 I capital B A. The 2's cancel off. And in fact, one better is, what would you call the little b times the little a? Yeah. And so that's capital A for the area. And so the area of that rectangle loop times the current times the magnetic field gives me the torque. So do I have a net torque? Yes. Is it going to spin? Yes. You saw this before. Maybe it's worth seeing again. Here it is. I have my loop. I have my wire. If I then take a set of magnets and I place the magnets on each side of those wires, I then, by passing a current through this wire, in fact, maybe I should take it apart and hold it up here. And you see what I have is I've got a metal nil that is then soldered onto this wire, and then it's wrapped around, of course, this time many times. We did the torque with just one wire. What do you think will happen if I wrap it around twice? Yeah, twice as much torque, and then 3 times as much torque, and 4 times as much torque. So we'll add multiple turns here in a second here, but this has been wrapped around a lot of times and then coming out the other side. So that when I place this in here and run current through it, the current will be going towards you. The magnetic field will be one way or the other. I'm not sure which way it is here. And then I guess we could measure it, but I'll just spin it and it'll go one way or the other way, okay? But there's a magnetic field. But the point is, it will then push this wire, let's say, to my left, and the bottom wire will be to my right. And so, as you saw last time, and hopefully we'll see again, if I plug in my electrodes here, current should go through those metal nails. It should, all right, got to plug it in first. Turn it on, and I guess I'll kind of crank her up here. I see if there's any, I think it wants to go. Yay! Okay, there we go. And so there's what Don and I affectionately refer to as our Flintstone motor. Okay, but it's obviously not a whole lot of power and a lot of current there, but it does kind of roll around and make sparks because things jump around, not well balanced. But clearly I get a torque. I get a net torque. And this is that last step of that I was saying, the last application. This is our electric motor. Now, what happens as it turns? What would it look like a moment later? That it was at this location, now it's at that location. Do you have the same torque? No, we don't. So let's do this all again, but this time put in an angle of rotation into it. And that's what the next picture is saying here. Let's take this motor and take a look at, say, this location. And what the author means then is right here, at this location, this may have rotated a small angle. And so they say, let this perpendicular line to the area. And so if you remember, we had an area vector when we did Gauss's law, right? We had an area and then a vector from it. So if you look at this contraption, you will see that there is the area, there's the A times the B, and so there is an area to this loop. And if you imagine a vector perpendicular to it, like my thumb, then that's what the author is trying to say. Look at the area vector. The area vector has a magnitude which is equal to the area of that loop, but it points in a direction that is perpendicular to the surface that is made by that loop. So I am saying it has then rotated. Well, maybe I said that wrong. It has an angle, I guess it rotated this far, but there is an angle theta between this area vector and the magnetic field. And that's what I want you to see. We're gonna measure our angle then in that sense. As this thing rotates around and we say, what angle is it? Our definition of the angle then is between the normal vector and the magnetic field. That's our theta. So if you do a little math in here, you can see that if this one is called theta, and then this one is 90 degrees, then this is the complement of theta. Which means then when you make a right triangle over here, this one is the theta. Now, here's why we're going to do that. Let's come back here and recalculate this. Okay? Let's come back and calculate the torque from wire number 2. What has changed, if anything? And there has been a small change. Not much, but a small, yeah.
I'm kind of confused about the eyes. Aren't the eyes different? Like the eye for torque is the moment of inertia?
Ooh, fair enough.
And the one over there, isn't that current?
Yes. Yes. I did not even notice that. This, maybe I should have just never put I for moment of inertia there and just say this is net torque. And so what I have just calculated is the net torque. That would be equal to, and then I won't put any more I's on the board, but that would be the moment of inertia times the angular acceleration. But you are right, and I want to make sure everybody hears that. This I here is the I for the current. The other I that I didn't really do anything with, so that's why I go ahead and erased it. But that was the moment of inertia of that rotating armature. Yeah.
And then one other thing, you said that for I for the current that we could ignore whether it was a proton or an electron.
Oh yeah.
And I was wondering why that is. Like you don't have to worry about the positive or negative sign.
Because the direction of the current is really, let's see, how can I say this well? Once you say the direction of the current is, and in this case, once I say the direction of the current is out of the board, okay? If positives are moving, then it's out of the board. But if negatives are moving, it is into the board, okay? So the positive and negative, the equal and opposite, is buried in the direction of the current. So I don't need to worry about it anymore when I do my cross product. That helps. It's already been taken care of when I get my direction for my current. Right. All right. So as I said, let's repeat this with a small angle, and you'll see there's a small change, but it'll emphasize the cross products. Right? There's two of them here. The first cross product would be the force from the magnetic force. Let's look at that one. Let's take a look at wire number 2 again. Wire number 2 is going towards you, right? So it has a current, it's in a magnetic field, it has a length of A, as we said. But what angle? What is the angle here? And this would be the angle between what? The wire and the magnetic field. What is it? Do you see it? Is it theta? Is it 90 minus theta? Is it 180 minus theta? How about none of the above? What is the angle? Isn't it 90 degrees? What way's the current? Which way's the magnetic field? What's the angle between those two? 90 degrees, isn't it? It's not even represented in this plane. The 90 degrees is this vector coming out and the magnetic field, which is this way. If I grab that little contraption, I guess it would look something like this. I is towards you. B is that way. And as it rotates, it's still 90 degrees. Fair enough? So the angle between the I and the B is 90 degrees and doesn't change as the crazy thing rotates. So when I come over here and I go to calculate the R and the F and the sine of the angle from this cross product, I would put the F as what I had before. An I, a B, and sine of 90 degrees, and an L, where the L is going to be that little a again. Fair enough? 90 degrees, no matter where it rotates. And in fact, as it is rotating, then let's look at R. Isn't R still B over 2? I mean, the distance on this radius doesn't change. As this thing sits in here and rotates around, it's still this distance, right? It's still B over 2. Wow, but sine of what? What's that angle? Is that 90? Theta? 90 minus theta? 180 minus theta? What is our definition of a cross product again? Well, I guess it's the angle between R and F. So where's R? Well, I guess from here to here is R, right? And there to there is F. So isn't this the angle between R and F right there? Isn't that 180 degrees minus that theta? And so I would say this is 180 minus theta. However, those are supplemental angles. So isn't a sine of 180 minus theta the same as sine theta? I mean, maybe it's worth writing it out, but sine of A plus B is the sine of A times cosine of B plus cosine of A sine of B. And if you put in 180 degrees minus theta, you will get, for the first one, sine of 180 degrees cosine of a negative theta, because I'm thinking of this as plus a negative theta. And then over here, did I do this right? Cosine of 180 degrees times sine of a negative theta. And so sine of 180 degrees is what? 0. That one goes away. Cosine of 180 degrees is what? Negative. So I have negative of a sine of negative theta. But sine is an odd function. So the negative of an odd angle, or a negative angle, is that angle again. All right, so this comes out to be B over 2 IB sine of 90 degrees, which I'll leave alone, L, which is A, and then sine of the angle between them. So one angle of the cross product is 90 degrees. The other one is the angle between them. And so what I get when it's all said and done, like we did before, is I can double it. So the total torque is 2 times B over 2 times I times B times A times sine theta. The 2's cancel off, and the little b and the big A I can call area. And so that would be the torque. So doesn't it look a lot the same, except what have I thrown in there? Sine of the angle. And the angle is measured from what? Right? The area vector and the magnetic field. Is there a place on here where I'd get no torque? Wouldn't that give me no torque? Because the force on this wire is that way. The force on this wire is that way. They are equal and opposite, and they are just pulling on the wire, but there is no torque because there is no angle. The angle in that particular case is this would be pointing down here, and when the area vector and the magnetic are in the same direction, that would be no torque. So in this position, I would get a lot of torque, and in this position, I would get no torque.
So what about the current traveling on the sides?
On here? Up here? Which we called 1 and 3? Right. We said there was no force on those, remember?
When it was in the initial position, but now...
Oh, okay, fair enough. Okay, so now I would come over to here, and you would say, okay, now there is a force on this, right? Let's see, and see if we can get the direction. So the current would be going, say, this direction. So I cross B would be pulling it up. I cross B would be pulling this one down. And there's no torque. There's a force on them, stretching them. And so these get pulled up. These get pulled out. Net force on the whole loop is still 0. And in this position, the torque is actually 0. So maximum torque, 0 torque. Okay? And so remember how we defined the angle. Now, if I did one more step here, I can finish the math and say, okay, here is the total torque on this motor. The total torque on this motor would be N, A, I, B, sine theta. What do I mean by N? Number of the loops. How many times did I wrap that wire around? Because notice in this, I don't know if I should call this a real motor yet, but the one that actually works, I did not just do one wire, I did a bunch of wires. Oh, I should bring a real motor. Next time I'll bring a real motor, we'll dissect it here. It's neat to see a couple of interesting things on how they get a lot of torque in a real motor here. But this is the torque here. And so notice then that the torque, of course, would change. In fact, your author makes one more step. He says, let's group this all together. Let's call this the magnetic moment. Let's give it a direction, and its direction would be the same as the area vector, so we can write it as a cross product. And so his final equation, and I guess my final equation will be this. Here is the torque from my electric motor. It is the magnetic moment crossed with the magnetic field. The magnetic moment being how big is the area of this rectangle and how much current is flowing. Those two factors we'll see come together a lot for the next 3 chapters. And so we'll group them together and start referring to them as the magnetic moment. What is the magnetic moment from, that wire on that current? Okay. And so there is your torque from your motor. Something a little clever here, maybe I should even point it out, we could run into troubles here because what would happen, so it started here, a lot of torque, gets it moving, no torque at this point. What happens here? Isn't the torque in the opposite direction now? So if the current continued to flow in the same direction, this would probably do something like this. Right? Because when it's in this position, if the current is still going down and the force is still going towards you, that's going to be slowing it down once it got started. And it's going to probably stop right about there. So if you looked carefully at the design of this crazy armature, you will hopefully notice that they've made a metal contact here, then break contact, and start up again. So that when it's in this position, if I were to plug this side into the positive, the current goes down this way and gets pulled out. But then when it gets to this position, it breaks contact and goes a little bit further, and look what happens when it goes back to this location. Notice that these brushings now touch this part of the commutator. And so now the current goes down this way. So we've used our mechanics, if you will, to make sure the current is always flowing down when it's over here on this side. Otherwise, we're just going to do that. Doesn't make a good motor. Okay? And so it swings back and forth.
So how does the brushless motor solve that issue?
Oh, they just have a small gap there, and they let the electricity flow through the gap.
So it's just going through the air?
Yeah. 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 And so you get really, really close. Here's a fun one. As you'll notice, the wire here goes through and goes here. There's no break in the commutator. How in the heck is this one going to work? I mean, if you hook this plus and this minus, it really would go like this. Well, we haven't got to alternating currents, but what if the current changed direction for me? What if the source changed the current, not the commutator changing the current? So this is what we will call an AC motor versus a DC motor. And so the current will go down, and as it rotates around, then my source will change positive and negative. And so the current will still go down, and it'll spin around. And the current will still go down, and the current will still go down, and the current will still go down. Yeah?
How do they get around the contact not wearing out?
Different approaches. This kind of homemade model obviously looks like it's going to wear out, right? You're going to see sparks flying. And when you ever look at a motor spinning, you'll see them. And like I said, I should bring a real motor. They usually make this out of a graphite. And so the electricity flows through the graphite. And the graphite is made, let's say this is the brushing. It's usually a long piece of graphite that is up against the commutator like this. And then behind it is a spring. So as it rotates, it wears out the graphite. But the spring keeps pushing more graphite close. And graphite is a nice dry lubricant. As it wears, it actually then has a very, very low resistance. So it's lubricating, and at the same time as it wears. Now eventually, these brushings are gonna wear out. I know that my table saw that I have replacement brushings, and it seems like every 6 years I've got to go down and go under the table saw, and it has a little screw hole. You pull it out, you pull out the spring, and at that point there's just a hair of graphite left, and then you go down to the store, and then you'll get a new piece of graphite with a spring, and you reload it, and tighten it in, and keep going.
Why don't they use brushless motors for the table saw?
Price. Dust.
Dust?
Yeah. Well, unless you enclose the brushings, keep the dust out. Yeah. But at least as far as I am aware, and maybe I should make this clear. I don't want you to think that this is the only type of an electric motor. Before this semester is done, we'll do probably 3 different types of electric motors, and then the world is just loaded with hundreds and thousands of different designs of motors. So there's a lot of neat things going on out there. And I suspect, given our state of energy and population, and a lot of you are going to be working in things that are what is efficiency, what is more efficient, what is sustainable, and so all these different designs are motors, so kind of center around that. This being kind of the first design and the simplest one to explain at this point. I see. Oh yeah.
So what would be the difference between The electric motors and the magnetic drive motors?
Let me answer that with an example. One of the examples I will do has a perfect one of that, although I don't think we'll quite get there today. But yeah, we've got a linear magnetic driven motor. We'll call it a railgun here in a second, and coming up. Yeah. So, all right. So I know there's not much time left, but at least let me do one or two quick examples here. We'll do number 1, number 3. Yeah.
Just a quick question. So this torque total, is this the total torque of an electric motor or just the total torque at an angle?
Oh, well, I guess this is the torque at that moment. All right, so that would be the angle. If I kept using my mechanics here, I would say this motor then is rotating. And so again, going back to, I guess it's chapter 10, our rotating objects, I can write this as an angular speed multiplied by time. And so this would be the torque of my motor as a function of time, as it is going around and around and around. And a lot of these motors, if we go back to my table saw as an example, is of course plugged into the wall. So it looks more like this than this. It's not a DC motor, it's an AC motor. And because the wall, it's plugged into the wall, the current goes back and forth. As some of you may know, I know we haven't done AC in this class yet, but there is a change. Anybody know the rate? 60 hertz, 60 times a second, which means in 1 minute it's 3,600 times. And so my table saw sits there and spins at 3,600 RPMs. That is the speed of my electric motor for hopefully obvious reasons, that is the rate at which the current goes back and forth. And if the motor tried to go faster than that, the timing of the current would be out of sync and it would slow it down. If it was slower than that, then the current there would be, if I'm saying this right, more of a push to get it to gain that speed. So it wants to go up to that speed, but doesn't want to go over that speed. It's the perfect match for it. Yeah.
So when they say 60 hertz, is that how many times it switches from positive to negative, or from positive to negative to positive?
One whole cycle. So
Okay.
I think what you're saying, positive to negative, back to positive. One complete cycle. Yeah. All right. Well, as I said, I feared that I was going to take a long time talking about all that. But if I jump into problem number 1, I like this one. Here's what it says. It gives you 4 different combinations, 4 different possibilities. It takes you back to the very beginning of the chapter, the force, the direction, and it says this. It says, what is the direction of the force on each of these moving particles? It shows you the particles and shows you their charge and shows you the magnetic field. So it reads this. Determine the initial direction of deflection of each charged particle as they enter into the magnetic field as shown. So if this is making any sense, let's look at A. A, we have a positive charge moving over to the right. We got a magnetic field going into the screen. Direction of the force is? Right. V cross B is up, and it's a positive charge, so it remains up when I multiply by a positive number. So there is A. How about B? All right, so V is this way, to the left. B is up. If I go V cross B, I would get into the board. Now, that's the cross product. But remember, the force is then times the charge. This being a negative, I got to multiply by a negative number, means the vector, the force vector would be out of the screen. So this would give me one out of the screen. C, no force. Why? Right, you might call it anti-parallel, you might call it sine of 180 degrees, or you just may say there is no motion perpendicular to the field. We only get a force when it's perpendicular to the field. And then finally D. Right? V cross B. V cross B into the screen. Right? And so the force, remember, has to be perpendicular to both of them. And this is my favorite one. You don't think that it's off at some angle. It's either into the screen or out of the screen. It has to be perpendicular to both vectors, the velocity vector and the magnetic field. So that means it's only either in or out of the screen. Yeah, I would say it's not as strong as it could be, because I would get its most force when its movement is exactly perpendicular. So it's not quite as strong as it could be, which I'm glad you asked that, because that's really the next one. Number 3 then says this. It says, here's what you have. Number 3 says a proton moves perpendicular. Maybe it's the one after that. This one is perpendicular. Okay. A proton moves perpendicular to a uniform magnetic field B. It has a speed of 1 × 10⁷ meters per second and experiences an acceleration of 2 × 10⁻13 in the positive x direction when its velocity is in the z direction. Determine the magnitude and the direction of the field. All right. Now, I grabbed this one because I like the way it kind of reversed things on you. In the sense that what I've done up until this point have been a lot of examples that said, here's V, here's B, give me F. But if you look closely at this one, it says, I'm giving you V. I'm also giving you F. Where's B? And so this one again says a proton is moving perpendicular to a magnetic field at a speed of 1 × 10⁷ meters per second. So that's the speed of the proton. It then experiences an acceleration of 2 × 10⁻13 meters per second squared. Huge acceleration, although fortunately not unreasonable, because these are such small masses, it doesn't take much force to result in a huge acceleration. Which is why when we were talking about the design of the TV and the oscilloscopes, these, I don't think I used the word oscilloscopes there, but these cathode rays are great because you can change it going to one direction to the other so quickly. I mean, the accelerations are incredibly large, as you can see, huge accelerations. But they say the acceleration is in the positive x direction. So let me put I hat here for the direction of the acceleration. It then goes on to say the direction of the velocity is in the z direction. So if I put a grid on here, this being x, this being y, and coming out of the board the z axis, I hope the first thing you realize is they have really told me the direction of the force. Isn't the direction of the force and the direction of the acceleration the same thing? Isn't that Newton's second law? All right. Force equals ma. All right, so there's the direction of the force. The direction of the velocity is this way. So, what direction is the field? Now, it says it's got to be perpendicular. I'm going with y. But is it in the positive y direction or in the negative y direction? Yeah. And so the B field is some number times a negative j hat direction, because again, in order to do the right hand rule, I would have to say V cross B to give me an x, right? And so the B must be down in that direction. And what would be the magnitude of it? Well, the magnetic force is QV cross B, QVB sine of 90 degrees, and I guess I better say, why do I know it's 90 degrees? Yeah, because that's said. Other than that, I wouldn't know. But it says the proton is moving perpendicular to a uniform magnetic field. And that would have to equal to ma. And so now I can put in my charges. Do I know the charge of the proton? What is it? 1.602 times 10 to the minus 19. Do I know the velocity? Yes, 1 times 10 to the 7th. Do I know the strength of the field? Well, no, that's what I would like to find, right? Do I know the mass of the proton? Yeah, 1.67 times 10 to the negative 27 kilograms. And then, do I know the acceleration? Yes, 2 times 10 to the 13th meters per second. So, using the right-hand rule, I can get direction. Using the magnitudes of the force with the acceleration of Newton's second law. Again, same idea. Did you notice I had to go back to my mechanics a lot here today? And that's what you're going to be asked a lot to do, to go back to your mechanics here. And then there's a bunch of examples I want to do for you. But I guess we're out of time for it today, so maybe more on Tuesday, and then even start the next chapter after that.
I thought that on a brushless motor, the